Welcome to the AI innovation space. We are your experts, and I'm Iyanu.
And I'm Todd.
We're here to offer our unique insights and hold conversations with top leading innovators in the world of AI and machine learning. This podcast is sponsored by Ellumen, an IT contractor offering a creative and human-centric approach to medical imaging, cybersecurity solutions, training and support, and more. Ellumen's values of ingenuity and connection make us a leader in adopting innovative technologies for federal healthcare and beyond.
Visit Ellumen's website at www.ellumen.com for an overview of the services offered and to read our blog series on leveraging AI for your business. Thank you so much for listening, and let's begin.
Awesome. So, Anton, I wanted you to introduce yourself, to our audience, and we'll get things started here. Who is Anton?
I'm an artificial intelligence engineer, and I do artificial intelligence and machine learning for one of the NSA leads at Artificial Intelligence, Lloyd Clark.
Thanks, Anton. I wanted you to share a little bit about, how you got into machine learning and artificial intelligence.
I'm a mathematician and a classically trained computer scientist. I started off as an electrical engineer, though, and basically I got exposed to Andrew Ng, and from there I basically got the basis of artificial intelligence using my mathematical skills.
Anton, you mentioned some of the math behind AI and deep learning networks. Any particular applications that you've worked on that you feel are interesting, or anything you'd like to maybe get involved in more in the future?
Well, I'm interested in the 3D point cloud convolution, sparse submanifold convolution for TensorFlow 3D. What it deals with is dealing with voxel spaces or three-dimensional data. And basically, you take this three-dimensional point cloud and you turn it into a sparse submanifold of the actual space. And then you basically do convolution. So you're able to do object detection, classification, and segmentation in a three-dimensional space. So that's the math I'm currently interested in right now.
Gotcha. At Ellumen here, right, we work on medical imaging, right? And so basically think about, or let me just use this hypothetically, right? Think about like medical centers, and what are some of the applications of AI imaging from your perspective to medicine?
So I've seen the melanoma challenge. I've seen the retina challenge. I think that the medical field provides a lot of very groundbreaking research into AI, specifically these images that are medical data, like tissue. Mm-hmm. Tissue is not very... The boundary conditions to do, like, let's say, a hue transform, which is one of the classical DSP, digital signal processing ways of finding edges. It's a lot harder to do on medical images. So your typical pixel counting, old school way of analyzing an image is a lot harder to do in this particular case. AI and medical imaging combined allows you to circumvent these problems. You shortcut that, right? And by using convolution or whatever ResNet or whatever respective artificial intelligence model that's able to basically find some similarity between an image by using deep neural network, that's where the power lies, right? Also, when it comes to mathematics and AI and things like that, the features or basically a lot of things like histogram filtering on images, or basically Gaussian transformations over the space, or some type of augmentation that optimizes the model's ability to basically gradient descent faster, or to minimize the loss between the actual label value and the predicted value. I think these techniques, and specifically the medical space, allow us to look at images where, in my field, I might look like at a deck board, or might be looking at a piece of steel. The work that's done in the medical field actually helps me because I'm able to look at what they've done, and I am able to say, hey, this image looks very like the distribution of pixels looks more like a medical image as opposed to me taking a picture of a dog in the grass, where the boundary conditions are very established. So I think that, like I said, the melanoma challenge, the retina challenge, A lot of these challenges provide a lot of very good architecture and ways of filtering, augmenting data for fields that have data sets that are very similar in terms of like, if you look at the mean of the pixels and the basically standard deviation in the pixels, and the boundary conditions or its ability to find edges, at those particular edge values, what's basically the difference from the mean, where they're very low in medical images versus like conventional, like, what we are like a picture. If I took a picture right now, me in a room, we'd be able to find the edge because the difference between me and the belt border or the wall or whatever, its deviation from the mean is higher, right? So that's where the value of medical imaging and processing and augmentation comes to great advantage to everybody in the AI field.
Like as you talk, right, I think about this application here, right? So, and I might be thinking, way over my head here, but think about a patient getting into the doctor's office, right? But then the doctor needs to examine this patient. Well, then the doctor doesn't have to touch the patient because they have sort of a three-dimensional representation, of the patient on the side. So, what do you think about that kind of application?
Yeah, you can do that digital twin. If the person had sensors on them and you basically were able to have a model basically create a digital twin of the particular thing that the doctor wanted to look at, very possible. I create digital twins on assets like motors and things like that. So very possible using sensors, cameras, and you just have the person hook up a sensor to them. You can monitor breathing. You could even do EKG, all type of things. Theoretically, yes. And I think people are working on it, but it's very plausible and very possible to create a digital twin.
I see. Oh, excellent. I will ask you about the how, but before we go there, to create these, digital twins, you think that there's a need for the Raspberry Pi, some type of chip, to help, with like the whole sensor aspect of it?
You could demo with Adafruit components or like Arduino components, but at some point you're going to have to go down to the hardware level and make your own sensors. So I develop hardware as well. So I'm a hardware engineer too. I build sensors. So at some point you're going to have to go down to the schematic diagram. You're going to have to examine like electromotor frequencies, disturbance, EMP, any electromagnetic disturbances due to equipment and things like that. So basically, when you're dealing with sensors in like even like a medical space, you have X-rays, you have radio waves, you have all type of waves circulating through the air. These waves can cause disturbances, especially on devices like capacitors that store energy, right? So the person designing the sensor has to be very cognizant about electromagnetic frequency disturbances that are in the air. In particular environments, especially hospital and medical environments, a lot of these equipments give off certain type of frequencies that you have to be cognizant of. So one, the developer of the sensor has to scan the area to basically find out if these things are in the air. And they have to design the sensor with respective to conditions like where is it going on the skin and blah, 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 blah. How does it mount onto the person? For example, accelerometer. If I put an accelerometer and the accelerometer is able to wiggle, right, that's extra noise that doesn't represent the data set. So things like that have to be taken into consideration. Now, an accelerometer could be used to successfully diagnose Parkinson's and other diseases that deviate where a person's human activity recognition deviate from the standard of what we label as normal, right? Mm-hmm. So when doing these sensors and things like that, those factors have to be taken into consideration. So some design to minimize noise or bias, B, epsilon, whatever, and also on a signal as well, to eliminate noise on the signal and bias on the signal as well, has to be taken into account. once noise is minimized, because if you think about the input is going to be input times some matrix, some coefficient plus or minus epsilon or bias. So in any linear LTI, linear time invariant system, right? So you think about a linear LTIs, linear time invariant systems, and how you process them. When you're dealing with sensor data, it's most of the time LTI. So whether it be vision, signal, or whatever. So all LTIs, you have to account for noise, and you have to denoise the signal. So and denoising occurs both at the hardware and the software level. So basically, when the designer is going into designing these sensors, that has to be taken into account. In my particular environment with motors and things like that, you have metal on metal. Metal on metal creates RF, radio frequencies, and these radio frequencies can interfere with the antenna and also discharge capacitors. So for the medical field, there's also these type of like devices and things like that. So those are some of the things that you have to take into account in the design process.
Excellent.
That's interesting, Anton. And can you expand on what kind of frequencies that you typically have to look for when you're denoising the signal, or any additional techniques that maybe you can share that you got to watch out for?
Yeah. So with LTIs and with frequency, so you have linear and you have nonlinear noise. With linear noise, you could typically use a RC or like a second order or a low pass filter to denoise. When the noise is non-linear, use what we call a fourth order Butterworth filter, either in hardware or software. It's very accurate at denoising non-linear interference, right? In my particular case, we get interference that basically interacts with the Wi-Fi antenna, so it could block packets from hitting a gateway, and it could also basically discharge capacitors from EMPs and basically throw the hardware into bootload mode. So those were two things that we had to pay attention for in terms of sensor data collection.
As we wrap up here, right? My question to you is, as Iyanuoluwa Anton want to build a minimum viable product, which means we don't want to probably use sensors, we don't want to build ours. We probably want to use what already exists. And basically we have chips, sophisticated chips that are able to do machine learning and things like that within such a way that we want to improve the healthcare system, right? Move everything to the IoT of things, using already existing, chipset and building them into, maybe an Arduino or whatnot, so that we are effectively able to have a minimum viable product. How do we go about that?
Yeah. So, if there is already medical equipment that you can integrate, you'd want some type of structured representation of the data. So let's say a heart rate thing that doctors might put on your finger, or medical images. You basically want to have this structured data in a way that could be inputted into a model as a tensor. That's the key thing here, right? And then also let's say these devices, let's say an X-ray device, or let's say a heart monitor, or let's say a stethoscope, or let's say whatever device, to build an MVP, you'd basically first have to create your data pipeline. So you have to go from sensor to, database to a database to be extracted to train a model, and then basically store the model, be able to ask the model a question and give you a pretty right answer, right? That would be the basis for the MVP, to make it viable, to make it a real product with machine learning, right? The question is, how would you get there using these sensors and equipments if they were pre-built? That would be it. You basically have to create a way to ingest the data, and send it from the device. If there's two ways. So the device might be using TCP, UDP, or some regular protocol or some serial way of sending the data, or might use some just JSONified XML or some way of sending the data like that.
So in this case, all that data would be then sent to maybe the Raspberry Pi that has the.
Well, why you even use a Raspberry Pi? Why not just use a surface mount AI chip?
Right. But what if you want to make it accessible maybe a viral phone or something.
You could do both. Like the ASIC can live anywhere. So like if the person needs real time data, like for example, the Surface on Edge GPU, like if the person's like, this thing is like critical, you can give them an answer on the device. You don't need to phone out anywhere, but you can still send the data back home and still do AI back home, but the person could get an answer right there.
Excellent.
Then you don't even need a Raspberry Pi. You can just dump it into the cloud if you have an ASIC on the edge.
Mm-hmm. Makes sense.
Because you're using a Raspberry Pi to do the ML, but you can do the ML on the device like now. So like, let's say like, if you go on Coral.ai and look at products, you'll see that they have a Surface Mount Edge TPU. This Edge TPU can do time series, image, all types of data processing.
Makes sense.
And can be just soldered on to a piece of hardware. And programmed.
Right. Makes perfect
sense. Yeah, the old paradigm is get the Raspberry Pi MVP. That's fading away.
Yeah, that's gone. Okay.
It's not gone. You can still like get an Edge CPU. Yeah, it's this new technology now. Like people, why phone home? Why worry about radio frequency interference? Why worry about an extra layer of communication on a bus? True. You know what I'm saying? If I can just look, if I can grab the image and then from the image sensor, take that image off the sensor and put it onto ASIC. You know what I mean?
Mm-hmm. That makes perfect sense.
Like OpenCV is doing that with the Oak.
Yeah, Anton, I'm just enjoying the conversation here. I'm just struggling to wrap it up, but, I would love to, probably, hear some really last words around, like, we have some of our audience that, don't necessarily have machine learning experience or whatnot. What would you suggest as the best way to get started in, this space, right? You have so much knowledge, I've spoken to you both online, offline. I know that a lot of people who listen, I would be really interested in knowing how they can get up to speed with, some of these things. So are there any pointers,
Yeah. I mean, so there's a huge movement with data science for all. And, shout out Permita. She has that movement, like different people. Me, I'm in the school of basically like, you have to do the math. You have to learn the computers. I'm more so cater for the people that really want to get into the field and not, like maybe have skills that they didn't discover yet. So I'm in the field of like, you might be good at math, but your whole life you thought you weren't. Or you might be good at logical, conditional logic, but your whole life maybe your social economic group is like math might not, why you need math? Math's not cool. Cause that's my story. Like, so, coming from certain ethnic groups where people might be like, math is not cool or blah, blah, blah. Like basically find out if you have the skill or not to do mathematics. And if you have the skill, don't take the cookie cutter way. Really try to learn the fundamentals of linear algebra. Really try to learn the fundamentals of like conditional logic of computers and things like that. Because as much as we want to put the training wheels on this thing, the gap between us and other nations is increasing drastically, exponentially, right? So I would encourage everybody to, one, there's some good books like Concrete Mathematics, start off with regular algebra, learn algorithms, grokking algorithms, the algorithm book. Like it's basically start at your GED level, math, then go to the high school AP level. What I do to practice is I get college exam books for math. So I get SAT prep for math. If you're an adult, get the SAT prep book and start prepping. Get your basic math, trigonomic identities, chain rule, basically, like slope, intercept form. You learn how to do FOIL. You learn your quadratic equation. You learn basically how to solve things, all your SOHCAHTOA, sine, cosine, tangent, hyperbolic tangent, and all these things because we use them in machine learning. That's the basic. Learn to get your linear equations, get your basically, linear systems. and learn how to solve them because we use linear systems and AI. And it's not that complex. This is all high school math, right? A linear system, right? Solving for a linear system. Basically, and from a linear system, I would go into some like understanding basic linear algebra, decomposition, like solving, a matrix problem, which is solving a linear system problem. That'll give you the basis and to keep pushing that next level. You don't need calculus for machine learning. You need linear algebra, right? So that's basically stacking on a bunch of high school math. And then on the other side, you need computer programming. Now, when I started computer programming, I learned in C, and it was very difficult as a kid. And like now you have all these resources. So I would say learn Python, learn C, learn languages. Don't take the easy route. I mean, that might sound contrary to what other people say, but I'm one of those guys that say that do the hard work and it'll definitely pay off or you could become a project manager, which is like the easier one. But now like people are pushing for more skilled project managers because now the project managers can't even hand wave anymore. You got to know what's going on. So I would say, deep learning AI, Andrew Ng. I'll get the Python, head first into Java, books like that. And then basically like concrete mathematics, grokking algorithms, algorithm book. GitHub is a great resource for machine learning and basically, go from there.
Awesome.
So you make some great points there, Anton, about learning math and learning computer programming to get into machine learning. Where do you see the industry kind of going in the next couple of years? Just thinking kind of more big picture. Let's say you have all these people learning all these skills you're talking about. Do you see it kind of being ubiquitous throughout industry or any? What are your thoughts?
The people without these skills are going to get left behind to some extent because what's going to happen is that the feature engineering part is the part where it gets really it gets real because feature, like let's say I had all these easy, I could make a model, no problem, right? But the model still needs to be data augmentation and some feature needs to be extracted that makes the data representation easier for the machine learning model to do. Now you went from training wheels to basically now I'm doing like linear algebra and filtering on a three-dimensional space matrix, right? So where's the space going? Like TPU, surface mount, ASIC, a lot of tools to deploy models, training pipelines, basically to automate the entire DevOps, right? So ML DevOps, ML Ops or what they call it. So automate that. But I still believe that the data understanding and the pipelining of the thing is going to remain like a thing where it requires these skills to have. And the guys with these skills that are able to go in and extrapolate features out data and data engineer on the spot, high speed data engineering. Because guess what? The data pipelines is going to get faster. The inference is just going to get faster. You're going to have to be able to do this thing at real time. It ain't going to be like the white papers where they do it and they get it done, but they ain't put the inference time. The inference time matters. It's going to matter in the future. And you got to have those skills to make these models run fast and to basically extrapolate these features. So in the future, I see like the edge TPU, the TPU, surface mount ASICs, where you don't longer have to phone home to the cloud or over the network to basically get inferences or train models. You can use back propagation, soft max regression on device.
That's awesome. So thanks so much, Anton, for coming.
Yeah, it was a real pleasure speaking with you, Anton. Appreciate you taking the time and going into a lot of depth on the math and aspects of ML that you do for your work. This has been the AI Innovation Space, sponsored by Ellumen. Thanks so much for listening.
Be sure to connect with us through LinkedIn and the Ellumen website to learn more about how AI and emerging technology can help you. Also, be on the lookout for our next episode coming soon. Thank you so much for joining us. Have a wonderful day.